Bismillahirrahmanirrahim. This is the third question from December 2019 exam of Canadian Professional Engineering Technical. Let's see what is the question. This is the circuit given. In figure, the switch was initially closed for a long time. So the switch closed for a long time. And at t is equal to 0, it is open. So we'll open the switch at t is equal to 0. And we have to find these four parameters, part 1. And this parameter, that is VCT, as part 2. Now this sequence is very confusing. You cannot find this one dV/dt or IC0 or VC infinity unless you find VCT. At least I don't know if there is any other technique. I could not find. So for what I have done is I have numbered these. Like the first one I'm calling 1A, then this is 1B, 1C, 1D. First of all, I'll solve 1A, and then I'll solve 2, and then I'll solve 1B, 1C, and 1D. So the first one, VC0. This is our circuit. Switch is closed. And when switch is closed for a long time, the circuit becomes steady state and the capacitor becomes fully charged and it behaves like an open circuit. So it will be an open circuit. And this voltage here, or the voltage across the capacitor, is called VC0 minus. That is just before the switch is open. And how much is the voltage, that it is not easy, or some student might have difficulty in finding. So what I have done, I have reversed the two positions. So the resistor is here and the capacitor arm is on the right hand side. Now you can see from here that whatever is the voltage here, the same voltage will be in this line and the same voltage will be across the capacitor because no current is flowing, so no drop in this resistor. Now how much is this voltage? From here you can very easily, by the voltage division rule, you can find that this voltage V1 is total voltage divided by the total resistance multiplied by 3 ohm. So it is 9.375. So VC0 minus is 9.375 volt. And now we turn the switch, or turn off the switch, we can say, remove the switch at t is equal to 0. And then whatever is the voltage across the capacitor will now be called VC0 plus. Now there is a very important property, and that is that the capacitor voltage does not change instantaneously. Whatever was the voltage here before the switch was before the switch was open, the same voltage will remain here after the switch is open. That means VC0 and VC0 plus and VC0 minus are same. So VC0 plus is 9.375 volt. So that is the answer of the first part. Now, as I mentioned, to solve the second part of this, we have to find actually part 2 of the question. Part 2 says VCT, that is the voltage across capacitor at any time t. We have to find. We have already found VC0, so we'll note it down here for reference. And if you go into the circuit derivation from the book, this is how it has been derived, the two currents, and then IC is CV dt, IR is V over R. From here you can write this, and then you integrating, we get this. And this is the final equation for a discharging circuit or a source-free circuit, where V0 is the initial voltage at 0 plus. Now, V0 we have already calculated from here, 9.375. What about RC? Find RC. Now this is open, so this portion is now redundant. We do away with this. This is the only portion left. And here the R is you can see this circuit is in series. So R will be 2 plus 3, 5. So RC we can calculate from here. 0.5 is R and C is 0.5. So RC is 2.5 second. RC is actually time constant it is called. So 2.5 second we'll put here. And V0, as I mentioned, V0 is actually V0 plus 9.375. So we put this value here and we put RC. And therefore, our VCT, that is the voltage across capacitor at any time t greater than 0, also called just Vt, is 9.375 e raised to the power minus t over RC, with 2.5 seconds. So this is our uh, general equation for the capacitor voltage. Now we go back to uh, question number 1, part B. Question number 1, part B says we have to find dV dt at 0 plus. Now we have Vt, so we just differentiate this with respect to t. So if you differentiate, you get this answer. I hope you know how to differentiate. This one will give us minus 1 divided by. And now at t is equal to 0, so we put t 0 or 0 plus. So this will be dv0 plus dt, and here for t we put 0. And we know anything uh, power 0, e power 0 is 1. Therefore, this will be solving minus 3.75 volts per second. This is question 1, part B. Now, 1C is asking IC0 plus. We have found these two. IC is the capacitor current at 0 plus time. We know the formula for capacitor current, dV dt. So at t is equal to 0, this will become IC0 plus, this will be dV0 dt. dV0 dt we have already found. We know the value of the capacitor 0.5. So this will be our IC0 plus, or yes, IC0 plus, minus 1.87. And the last question was to find VC infinity. Very simple. We have the formula of VC. We put t is equal to infinity. That will become at t is equal to infinity. This will become V infinity, and this will become, for t we put infinity. And I hope you know how to solve this, but just for those who have difficulty, this will be anything or the infinity divided by anything will be infinity. So we can write this as e raised to the power infinity, which can be written as 1 divided by e raised to the power infinity. E raised to the power infinity will be infinity. 1 divided by infinity will be 0. That means this whole term will be 0. And that means V infinity will be 0 volt. So this is the answer. But at the end, I will attach a simulation. I love the simulation circuit. And this gives you very interesting phenomena, how you can see the capacitor is fully charging, how is the capacitor discharging. So if you are interested, you see the simulation as well. Thank you. Okay, so this is our circuit. We are going to simulate. You can see the 5 ohm resistor, 2 ohm resistor, 3 ohm resistor. We have a capacitor of 0.5 farad, 500 millifarad. We have a voltage source, 25 volt. And to measure, I have connected an ampere meter here to measure the charging current, charging or discharging current. And also to monitor the charging voltage, we have connected a voltmeter. And you can see this in the scope also. Now, the question says that this switch is closed for a long time, and then we calculated this voltage to be 9.375. So let's see that first of all. Let me close this switch and let me run it. and we are running it at a high speed. So you can see the voltage is gradually increasing. From the graph also you can see from zero level it is gradually increasing, and this is the voltage level 5.5 now, 6. So keep monitoring this, and when it goes to 9.375, the charging current should stop and this should be level up. See, the current is gradually reducing. So we are nearing now 9.1. We need 9.375 as per our calculation for the capacitor to fully charge. You can see the current has reduced into milliampere, few milli, almost going to 0. We're looking for 9.375 here, and the current should stop. Nine point three seven four. And at 9.375 it is almost 0. See, should get 0. And you can see now this is almost a straight line. So the capacitor is fully charged at 9.375 and there is no more charging current. So this voltage we are calling V0 minus. And now when we open this switch, we are saying that V0 minus and V0 plus should be same for few uh, microseconds. So let me first of all slow down the speed so we can see it. And then I'll remove this switch, and then you have to see this voltage. After this switch is open, this should remain 9.375 for a few moments, and then gradually it will decrease because then the capacitor will now charge through, discharge through this circuit. So let me open this. Okay, so this has been opened and now you can see 9.375. It is holding, and now it is gone to 374 and gradually it will reduce very slow. Now this we are clear. So now let me just go it faster. So increase the speed. And you can see now it is discharging, it is going down. This is the discharge path. And the one of the answer question is what will be the V infinity? V infinity means for a very long time when the switch is open, and that means when the capacitor has fully discharged through this. So logically it should discharge to 0, and we'll see that. So you can see this is almost touched the 0 line. So the capacitor is almost discharged. You can see the discharging path. See the discharging current has reduced almost to zero. So this is V infinity, which we are saying V infinity should be zero. See the current has almost depleted completely. The capacitor is almost discharged. So I hope you have enjoyed this. You have watched this phenomena, how capacitor is charging and how it is discharging. Thank you. Stop it.